In this video, we'll be looking at the speed required for an object to orbit a planet in a perfectly circular orbit. So let's consider the object that's doing the orbiting, the mass of that to be the mass of a satellite. It could be a man-made satellite, it could be a natural satellite, like a moon. That will be orbiting in a perfectly circular orbit, some distance r away from some planet, which we'll call m sub p. Since it's moving in a circular path, we can use a formula we learned back in circular motion, which is net centripetal force is mv squared over r. Now think for a moment about what the m in this formula represents. That's right, that's the mass of the object that's moving in the circular path. So in this case, this m gets replaced with the mass of a satellite. And the r in here is the radius of the circular path that it's moving in. Now take a moment to think about what type of force is providing this net centripetal force. In other words, what kind of force is keeping the satellite in orbit and preventing it from moving off tangent to that circular path? Hopefully, you came up with the idea that the force keeping this satellite moving in a circular path is the inward force of gravity. So now, on the left-hand side of this expression, we can replace net centripetal force with F sub g. Take another moment here to think about what expression we might use for that force of gravity, knowing that the satellite is not on the surface of the planet, and we don't know what planet this is. Therefore, we don't know what little g is. Hopefully you realize we need to use the expression Fg equals g, mass of the planet, mass of the satellite, divided by the distance between the centers squared. If we take this expression, Newton's law of universal gravitation, and replace it for the left-hand side in our net centripetal force formula, we get g, mass of the planet, mass of the satellite, divided by the distance between their centers squared, equals the mass of the satellite times speed squared over the radius of this circular orbit. What do you see in that expression? That's right. The mass of the satellite appears on both sides and can therefore be canceled, which is interesting because it doesn't matter what is doing the orbiting in this, it's a circular motion. Additionally, the radius on the right-hand side cancels with one of the radii on the left-hand side, leaving us with an expression of g, mass of the planet, over r, is equal to the speed squared. Square rooting both sides gives us v equals the square root of g, mass of the planet, over r, which is an interesting expression because it says the speed of an object that's in a circular orbit around a planet depends upon the mass of that planet and the radius of the orbit that you are interested in, which may vary depending upon the type of satellite we would be sending up if it were a man-made satellite and its purpose and function. I think you'll find some other interesting things that this formula shows us as you go through some example problems.